Okay, now that you've tried all of these problems, let's look at number 20 and see how this works. Determine for which values of m, there's m is a number. The function, again, this is y equal, is a solution. Well, let's see what this says. This is a differential equation, second order, and it's linear. So if they're saying y equal e to the mx, then y prime is m times e to the mx, and y double prime is m squared e to the mx. That's how you take a derivative. If you substitute in, that is m squared e to the mx plus 6, a derivative that's m e to the mx plus 5 times e to the mx equals 0. I could factor e to the mx out of this. That would be m squared plus 6m plus 5 quadratic. So e to the mx can never equal 0, we know that. It must be that m plus 5 into m plus 1 must equal 0, indicating that m equal a negative 5 or a negative 1. And in case you didn't figure out what this means that e to the negative x and e to the negative 5x would be solutions to this equation. Something we're going to find in the next chapter. If I look at part B, well, it's saying the same thing. So this is A, that's B. Same thing, you're going to let y equal phi of x, which is e to the mx. A derivative I already found is right there. A second derivative is right there. I need one more derivative. So wouldn't y triple prime equal m cubed e to the mx? And if I substitute, wouldn't that be m cubed e to the mx plus 3 times m squared e to the mx plus 2 e to the m, no, 3 to m e to the mx equals 0. And wouldn't you say I could factor e to the mx out, and I will have m cubed plus 3m squared plus 2m equals 0. Well, we know that e to the mx cannot equal 0. It must be that m into m plus 2m plus 1, which means m will be 0, negative 2, and negative. That's all they want us to find here. But what this means, e to the 0 is 1, e to the negative 2x, and e to the negative x would be a solution to this differential equation. Each of those would be, each of them. Pretty cool, huh? Alright. Now, okay. On the next theorem, well, a very crucial theorem. Now we're setting up all the language, so we're kind of like working on all the terms. What does that mean? And we're going to apply. You're not going to see this until the coming chapters. That starts from chapter 2 and 3 mainly, but we'll see it a bit before and after. So look what this says. Here it says, consider the initial value problem. We have a derivative equals some function. So if I let dy dx equal this function, f is being this derivative, and the partial of this f with respect to y, if both of those are continuous on some rectangle, in which, so I want it to be continuous on this rectangle that contains that point right there. So something that we haven't looked at, we're going to really touch on. What does the initial condition imply? That contains this one. Then the initial value problem has a unique solution. Unique means one of a kind, and when we get to the next chapter, I'll show you what that means. Y, they like phi of x, and some interval adding an epsilon, a delta to the actual initial value right there. So basically, no matter where you go around it, it's still continuous. So let me see how this works. If I want to apply this on number 24, so the way it works, I take the derivative and I set it on one side, everything else on the other side. Now you do recognize that here, this is dy dt. This is continuous everywhere. So that's not a problem. And if I look at a partial of f, so this is my f. If I take the partial of f with respect to y. So if I take the partial of f in this case with respect to y, that would be just a t plus 0. This is continuous everywhere. So in this case, yes, they say determine whether theorem 1 applies, that the given initial value problem has a unique solution. Yes, theorem 1 applies. So all what theorem 1 says, if you take the actual given derivative and take the partial of that with respect to the dependent variable, if both of those, that derivative and the partial, are continuous on some interval, including this initial condition, then you do have a unique solution. So let me jump to number 28 in case you're wondering how could this not work. This is already solved for y, so I could call this f. So f, again right there, dy dx is f of xy. This is 3x minus cube root of y minus 1. That's continuous everywhere. No problem there. But what happens if I take the partial of that with respect to y? If I take the partial of f with respect to y, this is 0, this is negative, so this is y minus 1 to the 1/3. Bring the power down, subtract 1 from the power. That would be negative 1 over 3 cube root of y minus 1 squared. Now, are we in agreement that this is not continuous at y equal 1? That's the only point you can't have. But look, do you see what their initial condition is? Their initial condition, they say when x equal 2, y equal 1. Do you see that there's no way of including the initial condition because y equal 1 is not continuous? So here we say no, theorem 1 does not apply. And a unique solution is not guaranteed. Let me just see how they write it in the back of the book. They just say the theorem doesn't apply, but that's what it means. And if I look at this, and again, I'll work this out for you. I'll show you an example. Probably I'll come back to this problem and work it out for you once we get there. Not this problem. This is not separable. In chapter 2, I'll show you a couple of examples. So here, the same deal. If I say dx dt equal negative the cosine of x plus sine of t. Well, this is continuous everywhere. If I take, so if I call this f, if I take the partial of f with respect to x, the dependent variable, that will be the sine of x. That's continuous everywhere. So when you say I have a point of pi 0, you say, okay, well, this is continuous everywhere. No matter where this point is, this will always be continuous, this will always be continuous. So you say, yes, theorem 1 applies. And that means you're guaranteed a unique solution. There's only one solution to that equation. And let me give you the homework.